Now, do all operators commute? No, right? Um, Something that's interesting about commuting operators is that if one has, so let's say TV is equal to lambda V. In other words, let's say V is an eigenvector of T. Okay? In that case, then you have S of TV equals to Ts of V, and then because TV is lambda V, you have S times lambda V, and that gives you T of, let me see, yeah, T of SV. So that if I move this lambda outside, because S is linear, that's, you can write this. So if you have commuting operators, and V is an eigenvector, then V is an eigenvector of T, then SV is another eigenvector of T. Now, let's suppose that T has distinct eigenvalues. In that case, that forces SV to be some multiple of, so if T has n distinct eigenvalues, then it's diagonalizable. Every eigenvectors are linearly independent of each other. So that forces SV to be in the span of V. So SV would be some lambda, some k times V. Okay. So you stick that in, and of course it works. But this time, if you look at what just happened, is that if SV is equal to k times V, that means k is an eigenvalue and V is an eigenvector for S, right? So at least when all the eigenvalues are different, you can show that S and T has same eigenvectors, right? And it actually goes by the following theorem. If an operator is, if two commuting operators are separately diagonalizable, and diagonalizable is same as saying you have n distinct n linearly independent eigenvectors, right? So if T is diagonalizable and S is diagonalizable, then they are simultaneously diagonalizable. In other words, there's a basis where both SB is diagonal and also T is diagonal. In the case when you have n distinct eigenvalues, it's rather straightforward because of this kind of argument. For the case when you do have eigenvalues with multiplicities, it requires some more calculation, but you can do it. Okay, so that's something that we know about operators in general. In general, operators don't commute. If they do commute, then you have that they're diagonalizable under the same basis. There's a basis where you can diagonalize both of them at the same time. But then here's an interesting property that you might wonder. Does an operator T commute with its adjoint? Certainly this is true for self-adjoint operators. So definitely there are operators that would commute with its adjoint, right? But you can easily write down matrices that you can just write down generic matrices A, B, C, D and write this condition out and find a counterexample that doesn't work. So this doesn't always work. And therefore, you make a definition. The definition is 7.18. If for some operator T satisfies, if a T satisfies t star equals to t star t, we say t is normal. Now, it's a mistake to think about normal as like the antonym of abnormal. That's not the normal in this case. Normal here means orthonormal. Okay, so you'll see later that if t is normal, then you have the eigenvectors of t are orthonormal to each other. Okay, or orthogonal to each other. They're perpendicular. That's not the case. I mean, certainly we know that if you have two eigenvectors that have different eigenvalues, then they're linearly independent. But for this one, if you have eigenvectors that have different eigenvalues, then not only they are linearly independent, they are orthogonal to each other. Okay? So that's what normal is. Okay. In fact, normal. This is a closed condition. It's if you collect all the matrices that look like this from set of all possible matrices, this is like what's known as a hypersurface. Hypersurface? Yeah, it's a variety. This is an algebraic condition, so it's like oh, this is not a single equation, but it has like several equations together, right? So what that means is that if you randomly write any matrix, it's usually not normal. Okay. So there are far more non-normal matrices than normal matrices. Is that okay? All right. But then that might say, okay, well, if only some special ones satisfy this, why do we study this at all? Well, because self-adjoint is a special case of this. Okay, so anything that you prove for normal will be a theorem for self-adjoint. Okay, yeah. Most notably, over the complex numbers, the normal matrices have the property that you can diagonalize it. Okay, so that's what we want to prove. That's called the spectral theorem. Okay. All right. So what else can we talk about normal? First of all, we can show that T of V is equal to T star of V for all V of V. Okay, so let's try to see why that is so. So what is TV? Well, I'm writing this because this is the norm squared of TV, right? Okay. So let's see why. So maybe I should start with the left side. So I want to start with this and show that eventually this is the same as T star V. Okay. So I rewrite this as TV. And then I want to move this to the other side as the adjoint. It's not self-adjoint, so we still have to write down T star. If it was self-adjoint, it would just simply TT. Yeah, but it's not we don't know if it's self-adjoint, so it's T star T. But we do know that T star T can be switched, right? So I can rewrite this as T star V. But then this T here, I can move it to the other side by writing as T star. By using adjoint, I can move it to the other side. So that gives you T star V, T star V. Oh, these two are the same. So what's that? That's T star V norm squared. Done. So since their squares are equal and these are positive, if two positive numbers squares are equal, they themselves are equal, right? I mean non-negative. Could be 0. Yeah. So these are non-negative. Their squares are equal, so they're equal to themselves. Okay. So that's one thing. Now, that means 7.21, if lambda is an eigenvalue of t, then lambda bar is an eigenvalue of t star. I'm kind of questioning whether we need normal for this or not. See, T adjoint is complex conjugate transpose. Oh, wait. If it's transpose, we don't know what the eigenvectors are, right? Yeah. If it's complex conjugate, then we know that the eigenvalues will be just complex conjugate, right? So, so we do need normal. Okay, let's try to prove this. So what you do is, what does lambda being eigenvalue mean? It means TV is equal to lambda v, right? But then this is same as t minus lambda I v equals to 0. And then you take the norm. But the norm of 0 vector is 0, right? Okay, and then another thing is I is self-adjoint, of course, right? And the adjoint of I is self. That's something that we proved before. So if you multiply anything to I, it may not be self-adjoint, but it's still normal. Okay? So if you have see the problem is, if you have a self-adjoint operator and then you take some constant c to it and then you take the star of it, this becomes c bar t star because of the way you do the it's as I said, it's a complex conjugate and transpose, so there's this thing coming up. So if you multiply a real number to a self-adjoint operator, then it's still self-adjoint, but if you multiply a complex number, it's no longer self-adjoint. However, it's still what is it normal? Yeah, because this is still going to commute with CT, right? These two are still going to commute because these two are the same. Yeah. Any matrix commutes with itself, right? So any operator commutes with itself. So if t star is equal to t, then these two definitely commutes. So what I'm trying to say here is that because I is self-adjoint, lambda at I is normal, t is normal by our assumption, and if you have two normal operators, then any sum or subtraction or linear combination will again be normal. So I would say normal is nice in the sense that it's a weaker condition than self-adjoint, but you have more freedom to add or subtract or multiply some complex numbers, and you still stay normal. I guess that's one of the reasons why you want this. Okay, so you have that, and then t minus lambda I star v would still be equal because of this property that we just proved, right? If it's normal, then these two are the same. So we say this would equal to 0. But what does that mean? That means t minus lambda I, t star of lambda bar I star of v would equal to 0. The only vector that has norm 0 is the 0 vector, so this thing inside should be 0 vector. But then I star is I, so you end up with t star v equals to lambda bar v. Okay. So that's the interesting thing that you observe for normal. And probably the most important item here would be this last theorem, 7.22. If t star is t star t, if it's normal, and t TV is lambda 1 V, and TW is lambda 2 W, VW non-zero, and lambda 1 is different from lambda 2, then V and W are orthogonal to each other. Okay, and orthogonal, you know, when in space, when you have a plane and a line that's perpendicular, you say it's normal, right? Yeah. So normal is another word for saying perpendicular, and this is exactly why we call such a property as normal, right? Let's try to prove this. So proof. Well, we have to use this some way, so let's take TVW and see what happens. Okay. All right, so TV would be lambda 1V W, and then this is going to be lambda 1 VW. Okay, so that's one way. Oh, there's something that I forgot to say here. If V is an eigenvector for T, then V is again an eigenvector for T star with the complex conjugate. Okay, so I should have wrote this down as well. So they have the same eigenvector, except that their eigenvalues are complex conjugated. Okay. So the reason I say this is because this is also equal to, I can move the T to the other side, right? So I have V T star W. But then T star W is what? Well, TW is lambda 2 W, so that means lambda 2 bar W is what you get for T star W because of this lambda. If W is an eigenvector for T, then W is also an eigenvector for T star. The only difference is that instead of lambda as your eigenvalue, the lambda bar is the eigenvalue. Okay, so that's what we have. But then when this comes out, what is that? A complex conjugate comes out, and if you have double complex conjugate, it comes back to the original one, so you get VW. Okay, so because I computed this in two different ways, these two must be equal. Okay? And now what do you see? You see that if I move this to the other side, I get lambda 1 minus lambda 2 VW equals to 0, and because our assumption is that lambda 1 and lambda 2 are different, that forces V and W to be equal to 0. Okay. Now, although the spectral theorem is proved more generically in a different approach, this thing itself already shows that if you have a normal operator with n distinct eigenvalues, then you have an orthonormal basis which diagonalizes it. Okay? We already know from a few lectures ago that if you have n distinct eigenvalues for an operator, then you can diagonalize it using some basis, but we don't know if it was orthonormal, right? Normal, a normal operator has an orthonormal basis which diagonalizes it. Okay, so that's the statement of spectral theorem, and you can kind of like argue this heuristically. So if you're given some normal matrix where you might have an eigenvalue that has multiplicities, try to add a slight epsilon to one of these to like deform this slightly so that the eigenvalues are slightly different. Okay, because the having equal eigenvalues is a closed condition, you can just move away from that point slightly, and then now you're in the case where you have n distinct eigenvalues, and then you can always diagonalize it, and then you send this limit where the eigenvalues end up being equal, and that's like a heuristic, not really a rigorous argument, but that somehow you can show that any normal matrix or any normal operator can be diagonalized under some orthonormal basis. Okay.